All right, welcome back everyone to another edition of Lessons in the Alphabet. So we take different combinations of the Latin and Greek alphabets and try to combine them in odd equations that tell us something about economics, right? So that's what we're doing in this class. Okay, so happy Wednesday if you're watching this on class time on Wednesday. And I wanted to go through some more examples of our newly acquired skill to handle inequality constraints. And so last time in class we did consumer maximization problem where I bought two goods, beer and pizza. They each had a price. I had some income and I had to decide how do I divvy up consumption between the two goods. And we kind of derived a general solution. So we also discussed as a possibility we could look at consumption and leisure choice. And that's what we're going to do in this video. So we're going to decide between consumption and leisure. And so some of you have had me for intermediate macroeconomics. And so you had some exposure to this basic idea, but let me just kind of re-explain it to refresh your memories. And if you haven't had me for intermediate macroeconomics, then you'll have a sense here of what the model looks like. So the basic idea is that I get C as my consumption. And so, so that could be of any particular good that you want, right? So we'll just call this pizza. So that's what I like to eat is pizza. L is leisure time. So what's the time I spend enjoying myself? So what's the fundamental trade-off in this model is that H is the total time available. And so the idea here is that of my total time, I'm going to divide it between working, call that NS, my labor supply, and the time I spend in leisure. So my basic budget constraint, so I'm also going to add what I call I, which is just other income. Right? So in intermediate macroeconomics, if you had taken that from me, other income was profits or dividends minus taxes. But here I'm just going to be more general. And so in this framework, and W is the wage, in this framework, we can write down a budget constraint, very similar to what we did with pizza and beer. Right? So now my two goods instead of pizza and beer are consumption and leisure. And so my budget is that my consumption has to be less than or equal to my total income, which will be my wage times, so this is labor earnings. Right, so I take my hourly wage rate times the number of hours I work here, which is the total time available minus L. So that is my labor supply. Plus then I have any other additional income, right? So perhaps your parents give you money, right? So your parents send you a check every month to cover some of your expenses. That would be part of your other income. Or perhaps I have, won the lottery, or I have some accumulated assets that provide me with some additional income. So my budget constraint says that my total consumption of pizzas has to be less than or equal to my available resources. And the only difference here between this one, in a sense, and the previous one is that you have some control over what your resources are in your choice of leisure. So I'm going to rewrite this budget constraint as if I add the WL over as consumption plus W times L less than or equal to WH plus I. So in this sense, I'm buying here consumption and leisure, where the price of consumption is 1. So this says the price of consumption is 1. The price of leisure is W. And that makes sense, right? So every extra hour of leisure I take, I work 1 less hour, which means I earn W fewer pizzas that I can buy. So W is what we say the opportunity cost of leisure. So that's my budget constraint here, is C plus WL has to be less than or equal to my total resources, which is available time, plus my other income. Okay, and so I'm going to add one extra constraint now to make this a bit interesting, which is that, well, L cannot be bigger than H. That's a pretty sensible constraint, right? If H is the total time available, L certainly can't be bigger than that. Now, what makes this interesting, right, is that that second constraint, in a lot of cases, probably isn't going to bind, right? I want to have some labor income, and if I have any labor income, L is going to be less than H. And so now we've got two constraints that make the problem a little bit more interesting to analyze. So my utility, and we're going to do an example here then, is over consumption and leisure. And we'll stick very close to what we did with beer and pizza. In fact, if you take these prices and you just call this whole other side over here I, you can map this problem exactly into the previous one we just did, right? With now we have this additional constraint that we can only buy so much of the one good, okay? So let's put some specific numbers to this to solve out an example and work through the different cases that we talked about. So let's set A equal to 0.1, W equal to 0.1, H equal to 100. So I have 100 total hours available. And every hour I work, I earn 1/10 of a pizza. That will set my other income equal to 50. Now, you can probably guess, before I even solve the problem, I look at those numbers, and I'm kind of setting up something in particular here, right? So notice A, this preference parameter A, is 0.1. Well, that says I don't put a lot of weight on my utility from consumption of pizza, but I do put a lot of weight on my utility from consumption of leisure. So that's already in favor of leisure. 2, leisure is pretty cheap. Every extra hour of leisure I take, I only give up 1/10 of a pizza. So there's not that much value of working. And 2, I have a lot of other income already available relative to that wage, right? So you can kind of see I've set this up where I'm going to want to take a lot of leisure. And so we'll see if that's enough to cause us this second constraint to be binding. And then we can think about an example where that second constraint won't be binding. Okay, so let's work through this under these assumptions and set up our Lagrangian. And we're going to now have two multipliers that we have to keep track of. Okay, so we'll get to that. So A is 0.1 natural log of C plus 1 minus A is 0.9 times the natural log of L. Then I have minus, I'm going to call it lambda 1 times my budget constraint, which is C plus WL minus WH minus I. So that's my budget constraint. And then I have minus lambda 2, and it is L minus H. Right? My second constraint is that L has to be less than or equal to H. So the only difference, we can handle as many constraints as we have. Too many constraints, it gets a little bit more complicated. And so if you get more constraints than choice variables, then you know only some combination will bind. Okay, so we have the Lagrangian, and now the path forward is pretty easy. So we're gonna take the first order condition, set it equal to 0, and then we work through the different cases of the constraints binding or not, and we have different complementary slackness conditions, etc. right? So in my steps, the next step is to differentiate these with respect to the choice variables, consumption and leisure. So the partial Lagrangian with respect to consumption, 0.1 over C, nothing there. We have minus lambda 1, and then we have nothing in the lambda 2 term, and that has to be equal to 0. All right, then I'm going to differentiate the Lagrangian with respect to L, and I'm going to get 0.9 over L minus W times lambda 1. And then I also have the minus lambda 2. Has to be equal to 0. All right, and then we have the various complementary slackness conditions. So I'll write those down just to kind of remember. Sorry, so we do know what W is and H is and I is. So I should have put these into my constraints. So I'll do that now. So 0.9 over L minus W was 0.1. Lambda 1 minus lambda 2 equals 0. And so I could write that constraint up there as C plus 0.1 times L minus, well, it's going to be, where are my numbers? Okay, so L was, or I was 50, right? Oh, there it is, yeah. So it's minus 60. So WH is 0.1 times 100, so it's 10, minus I, which is 50, so we've got minus 60 there. And this is L minus 100 down in the end. So I'm just filling in the actual numbers that we know right now. Okay, so then my complementary slackness conditions. Well, those say that the multipliers have to be positive. Lambda 1 has to be greater than or equal to 0. And then lambda 1 times my constraint, C plus 0.1 L, WL minus 60, has to be 0. So in other words, if the constraint doesn't bind, then lambda has to be 0. If the constraint does bind, lambda could be 0 or positive. We know that the other lambda has to be positive, and that lambda 2 times L minus H, which is 100, has to be 0. So if L is less than H, lambda 2 has to be equal to 0. Okay, and so our next step then is to take our different cases. And so we have a few different cases. So one case is that the budget constraint binds. So C plus 0.1 times L is just equal to 60, which is my total available resources, W times H plus I. So we're going to assume that binds, and then we have another constraint, and we'll say that the other one is slack. I'll call it the L constraint is what we say slack or inactive, which says that L is less than 100. That's H. So that's one case, is that the budget constraint binds, the L constraint is slack. We have other cases. Case 2 would be budget binds and L binds. So L is equal to 100. That constraint binds. Then we have all the other permutations, right? So the budget constraint is slack. The L constraint is slack. None of them bind. In case 4, so let's do case 3. None bind. And case 4 is that budget is slack and L is equal to H. the second constraint binds. So those are 4 cases. Now, as we discussed last time, we pretty much know that the budget constraint is going to have to bind, right? So our just basic economic intuition and logic says if the budget constraint doesn't bind, I can just increase how much I have of either consumption or leisure. I can do that by a small amount. My constraint still holds, and I'm going to get more utility, right? So I can always increase consumption if my budget constraint doesn't bind. So we're basically going to forget about case 3 and case 4 because they're both cases where the budget constraint is slack, and we covered that last time, right? We basically said in our 2 good example, beer and pizza, the budget constraint should bind in equilibrium, right? Or not in equilibrium, but the optimal solution. Okay, so let's handle case 1 with these values. Let's assume that the budget constraint binds, and let's solve them. So we're going to set lambda 2 equal to 0. So in case 1, the budget constraint binds. So I don't know. I mean, there are these weird cases where the constraint can bind and lambda is equal to 0, but I can't exactly rule that out yet. So I can't toss lambda 1 out. But because L is strictly less than H in our assumption, I can set lambda 2 equal to 0. That's the complementary slackness of case 1. If that constraint is slack, L is less than 100, lambda 2 has to be equal to 0 here in order to make my complementary slackness condition hold. So let's take our first order conditions with lambda 2 equal to 0. And what we get was, you'll have to kind of look back, our first order condition was 0.1 over c minus lambda 1 equal to 0, which means that lambda 1 is equal to 0.1 over c. Then our second condition was this one, 0.9 over L1 over L minus 0.1 times lambda 1 minus lambda 2 equal to 0, and the lambda 2 in this case is 0 because of our assumption that the second constraint is slack. So that means that 0.9 over L is equal to 0.1 times lambda 1. And lambda 1 is 0.1 over c. All right, so let's plug that in. So we have 0.9 over L is equal to 0.1 squared over c. And I can solve that for either c or L. Doesn't make any difference. Let's go ahead and solve it for c. (0.1 squared over 0.9 times L. If I did that correctly, which if you want the general version of that at this point is, let's see, so right now we've got A times W over 1 minus A times L. If I hadn't plugged in the specific numbers, and I might put a general case of this in another video. All right, so hopefully you're still with me here. So I solved for consumption as a function of leisure. And so it looks like, yeah, we'll just kind of leave that as is. So I mean, it's yeah, so that's 1 over 90 basically. Here, so C is equal to 1, well, L over 90. If I take 0.1 squared divided by 0.9. That's 1 over 90. So I've got L over 90 there is my consumption. All right, so then I plug that into the budget constraint, because in this case the budget constraint binds, and so I can use that, right? If the budget constraint didn't bind, lambda 1 would have been equal to 0, and we could solve the two first order conditions for C and L directly. In this case, lambda 1 is not necessarily equal to 0, and so when I plug this into my budget, which is C plus WL, WH plus I. So C is L over 90, W is 0.1 times L, WH plus I is 60. And so I can now just simply solve that for L. L times 1 over 90 plus 1 over 100 is equal to 60. L is equal to 60 divided by 1 over 90 plus 0.1. And if we calculate that, we get 540. Is my consumption, or my leisure, and I could plug that back in and divide it by 90, and I get C. C star equals L star divided by 90. And so that's going to be, what, 6 is my optimal consumption. And so hopefully this kind of helps, right, to see a specific example. So we solved it out, found that I want to take 540 hours of leisure and consume 6 pizzas. Any problems with this? Pause for effect. Yes, there is a problem with this, right? L, by our assumption, in this case, was less than 100. If we make that assumption, we find it's optimal to set L equal to 540, which is much greater than 100. L star is 540, is greater than 100. As I said before, that is a contradiction. That cannot happen. So, what are we left with? We're left with, well, case 2 has to be the only available option left in this case, right? So case 2 says that L is equal to H. Both constraints bind. And so this one's really easy to solve, right? I already know what L is. L is equal to H. And so my first order conditions really aren't necessary in this case. Well, they're necessary in the traditional sense, but I don't need them to solve out what the optimal solution is. I certainly could solve those combined with the two constraints, but since L is constrained to be equal to H, I know that in this case, L star is 100. C plus 0.1 times 100 has to be equal to 60, which is WH plus I, so C has to be equal to 50. Right, and so with those two numbers, I could plug back into my first order conditions and verify that lambda 1 and lambda 2 are in fact positive, which is what we would need in this case, lambda 1 and lambda 2 to be greater than or equal to 0. So let's just check that. Which is the last little bit to go with. And so our first order condition for lambda 1 up above was this. And so I, plug in there, and I've got 1 over 500 is equal to lambda 1, which is definitely positive. So we're good there. And then I can take that number for lambda 1. I can plug it into that first order condition for L. Way back up here, which was this one. And find lambda 2. So 0.9 over L minus W times lambda 1 minus lambda 2 equal to 0. So my other first order condition, 0.9 over L minus W times lambda 1, which is 0.1 over 50, minus lambda 2 equal to 0. L was 100, 0.9 over 100, minus 0.1 squared over 50 is equal to lambda 2. Now you can calculate that out, but I can see that it is going to be positive, or it should be. We can give you the exact. Is 0.088. Is my lambda 2, which is positive as required. So 3 check marks. Case 2 works, right? And now, technically, like I said, we should go back through case 3 and case 4, but we're going to run into contradictions there because they both assume that the budget constraint doesn't bind. And we've kind of logicked out that the budget constraint should bind. So I'm going to be a little bit sloppy in the sense that I won't check those 2 cases, only because in our previous example, we verified that the budget constraint had to bind. So with all this work, I now know that L star is 100. And C star is equal to 50. So hopefully this provides you with a little bit of insight into how these problems work. Another practice example. And what I'm going to do is I'll post a problem here, another version of this problem, same one, with slightly different numbers. And you'll have to go through these 2 cases again and see which one is most appropriate and which one gives you the highest possible utility. So in these examples, it's pretty straightforward because assuming one of the 2 cases typically leads to a contradiction. They both can't be true at the same time. As we'll develop a little more elaborate examples in the next couple of weeks, that won't always be the case, and so we'll have to get in the habit of always checking these cases. So there we go. I hope that, it's a weird thing to say, I hope you enjoyed this, or I hope this was helpful in some way, shape, or form. I'll post these notes. I'll give you a practice problem to work on. If you can handle that practice problem, then we're in really good shape. All right. I will see you probably virtually again on Friday.